Hi, this is NAVNEET REDHU. Today I am going to discuss NBHM PhD 2019 questions of topology section, questions 3.2 part B. Okay, what was the question? Question is nothing, basically X B any set is given, Y is Hausdorff given, and F is a mapping from X to Y, and he define U is a subset of X to be open in X if and only if U equal to F inverse V for some open set V in Y, and he is asking this define a Hausdorff topology on X. This statement is true or false. This was the question. Okay, now to check this is Hausdorff topology on X, first we have to check this is topology on X, and that is very easy because it define a topology, very special name called weak topology on X. Weak topology on X. Weak topology in X such that F from X to Y become continuous. Okay, this define weak topology on X. And how to check it? It's just three simple steps. The first is phi comma X is R open in X. This has to be open in X, and that are very easy to check because phi is inverse image of phi. This phi is a subset of Y, and X is nothing but inverse image of Y, and Y is also open in Y. Therefore inverse image of that is open in X, that's X is open in X, and F inverse of phi is also phi is open in anyway Y. Okay, now first condition is true. Second condition, you can check that intersection of two open set is open in X. You have to verify that. That is again very easy, checking F inverse of U intersection F inverse of U1 and U2. This is nothing but F inverse of U1 intersection U2, and this is open in Y, so this is open in X. And again third property is that is arbitrary union of open set is open. That's you can verify. That is very easy. Now the questions is whether it is Hausdorff or not. Okay, if the statement is true, that is if this define a topology on X Hausdorff, then it is true for every F. Any F you take from X to Y, it has to be going to true. If this is not true, what it means? We have to fail it for at least one F such that this does not become say Hausdorff topology, and that is very easy example. Take F from X to Y and define Fx equal to C for some C belongs to capital Y. Okay, that is a constant map, basically constant map. Now if this map is constant, then what are the open set in X? Let V be any open set in Y. Let V be any open set in Y. If V is open set in Y, then its inverse image is open in X. That will imply F inverse of V is open in X. Okay, this will be the case. Now F inverse V is equal to empty if C do not belongs to V, and this will going to be equal to X if C, sorry, there C does not belongs to V and here C belongs to V. Okay, Now whatever open set you take in Y, the F inverse V equal to either phi or X. Phi in case if C does not belongs to V, and X if C is in V. Okay. Now from here we see that phi and X are the only open set in Y, in X. Okay, phi and X are the only open set in X. This means it define a indiscrete topology. This means it define a indiscrete topology on X. It define a indiscrete topology on X, and we know if cardinality of X is greater than equal to 2, then it never become a Hausdorff. Then it is not Hausdorff. Why? Because we take any two distinct point X and Y in X such that X not equal to Y. We do not find two disjoint open set containing X and Y, because the only open set containing X and Y is X. Therefore this is not Hausdorff. So therefore the given statement is false, because he is saying that whatever mapping we take from X to Y and we define the weakest topology on X, such that F become a continuous, then this define as the topology on X. No, this is not true, because we see in case of constant function it will fail. Okay, thank you.